Today we are going to start with chapter number 7, Systems of Particles and Rotational Motion. In the earlier chapters, we primarily considered the motion of a single particle. A particle is ideally represented as a point mass having no size. We applied the results of our study even to the motion of bodies of finite size, assuming that motion of such bodies can be described in terms of motion of a particle. Any real body which we encounter in daily life has a finite size. In dealing with the motion of extended body of finite size, often the idealized model of particle is indicated. In this chapter, we shall try to go beyond this inadequacy. We shall attempt to build an understanding of the motion of extended bodies. An extended body in the first place is a system of particles. We shall begin with the consideration of motion of the system as a whole. The center of mass of a system of particles will be a key concept here. We shall discuss the motion of the center of mass of a system of particles and usefulness of this concept in understanding the motion of extended bodies. A large class of problems with extended bodies can be solved by considering them to be rigid bodies. Ideally, a rigid body is a body with perfectly defined and unchanging shape. The distance between all pairs of particles of such a body do not change. It is evident from this definition of a rigid body that no real body is truly rigid, since real bodies deform under the influence of forces, but in many situations the deformations are negligible. In a number of situations involving bodies such as wheels, tops, tail, beams, molecules and plants, on the other hand, we can ignore that they bend or vibrate and treat them as rigid. What kind of motion can rigid body have? Let us try to explore this question by taking some examples of the motion of rigid bodies. Let us begin with rectangular block sliding down inclined plane without any sidewise movement. The block is taken as a rigid body. Its motion down the plane is such that all the particles of the body are moving together. That is, they have the same velocity at any instant of time. The rigid body here is in pure transactional motion. In pure transactional motion, at any instant of time, all particles of the body have the same velocity. Consider now the rolling motion of a solid metallic or wooden cylinder down the same inclined plane. The rigid body in this problem, namely the cylinder, shifts from the top to the bottom of the inclined plane and thus seems to have transactional motion. But as figure shows, all its particles are not moving with the same velocity at any instant. The body therefore is not in a pure transactional motion. Its motion is transactional plus something else. In order to understand what this something else is, let us take a rigid body, so constrain that it cannot have transactional motion. Most common way to constrain a rigid body so that it does not have transactional motion is to fix it along a straight line. The only possible motion of such a rigid body is rotation. The line or fixed axis about which the body is rotating is its axis of rotation. If you look around, you will come across many examples of rotation about an axis. A ceiling fan, a potter's wheel, a giant wheel in a fair, a merry-go-round, and so on. Let us try to understand what rotation is. What characteristics rotation? You may notice that in rotation of a rigid body about a fixed axis. So here we are having a rigid body rotation about the z-axis. Each point of the body, such as P1 or P2, describes a circle with its center on the axis of the rotation. The radius of the circle is the perpendicular distance of the point from the axis. A point on the axis like P3 remains stationary. Every particle of the body moves in a circle which lies in a plane perpendicular to the axis and has its center on the axis. Shows the rotational motion of a rigid body about a fixed axis. Let P1 be a particle of the rigid body, arbitrarily chosen and at a distance r1 from fixed axis. The particle P1 describes a circle of radius r1 with its center C1 on the fixed axis. The circle lies in a plane perpendicular to the axis. The figure also shows another particle P2 of the rigid body. P2 is at a distance r2 from the fixed axis. The particle P2 moves in a circle of a radius r2 and with center C2 on the axis. This circle too lies in a plane perpendicular to the axis. Note that the circles described by P1 and P2 may lie in a different planes. Both these planes, however, are perpendicular to the fixed axis for many particles on the axis like P3 r equals to 0. Any such particle remains stationary while the body rotates. This is expected since the axis of rotation is fixed. So here we are having some of the examples of rotating body at a fixed axis. This is a spinning top. The point of contact of the top with the ground, its tip O is fixed. Axis of oscillation, here also we are having a table fan with rotating blades. The pivot of the fan point O is fixed. The blades of the fan are under rotational motion, whereas the axis of rotation of the fan blades is oscillating. In some examples of rotation, however, the axis may not be fixed. A prominent example of this kind of rotation is a top spinning in a place. We know from experience that the axis of such a spinning top moves around the vertical through its point of contact with the ground, swiping out a cone as shown in figure. This movement of the axis of the top around the vertical is termed precession. Note the point of contact of the top with the ground is fixed. The axis of rotation of the top at any instant passes through the point of contact. Another simple example of this kind of rotation is the oscillating table fan or pedestal fan. You may have observed that the axis of rotation of such a fan has an oscillating sidewise movement in a horizontal plane about the vertical through the point at which the axis is pivoted. While the fan rotates and its axis moves sidewise, this point is fixed. Thus, in more general cases of rotation, such as rotation of a top or a pedestal fan, one point and not one line of the rigid body is fixed. In this case, the axis is not fixed, though it always passes through the fixed point in our study. However, we mostly deal with the simpler and special case of rotation in which one line is fixed. Here we are having motion of a rigid body, which is a pure translation, and motion of a rigid body, which is a combination of translation and rotation. Figure 7.6a and 7.6b illustrate different motions of the same body. Note, P is an arbitrary point of the body. O is the center of mass of the body, which is defined in the next section. Suffice to say here that the trajectories of O are the transitional trajectories TR1 and TR2 of the body, and the positions O and P at three different instants of time are shown by O1, O2 and O3, and P1, P2 and P3 respectively. In both figures 7.6a and b, as seen from figure 7.6a, at any instant the velocity of any particles like O and P of the body are the same in pure translation. Notice in this case the orientation of OP, that is the angle OP mixed with a fixed direction, say the horizontal remains the same. Alpha 1 is equals to alpha 2 is equals to alpha 3. Figure 7.6b illustrates a case of combination of translation and rotation. In this case, at any instance, the velocity of O and P differ. Also, alpha and alpha 2 and alpha 3 may all be different. Thus, for us, rotation will be about a fixed axis only unless stated otherwise. The rolling motion of a cylinder down an inclined plane is combination of rotation about a fixed axis and translation. Thus, the something else in the case of rolling motion which we referred to earlier is rotational motion. You will find figure 7.6a and b instructive from this point of view. Both these figures show motion of the same body along identical translation trajectory. In one case, figure 7.6a, the motion is pure translation. In the other case, it is combination of translation and rotation. We now recapitulate the most important observation of the present section. The motion of a rigid body which is not pivoted or fixed in some way is either a pure translation or a combination of translation and rotation. The motion of a rigid body which is pivoted or fixed in some way is rotation. The rotation may be about an axis that is fixed or moving. We shall in the present chapter consider rotational motion about a fixed axis only. Center of mass. We shall first see that the center of mass of a system of particles is and then discuss its significance. For simplicity, we shall start with a two-particle system. We shall take the line joining the two particles to be x-axis. Let the distances of the two particles be x1 and x2 respectively from some origin O. Let m1 and m2 be respectively the masses of the two particles. The center of mass of the system is that point C which is at a distance x from O, where x is given by x is equals to m1 x1 plus m2 x2 divided by m1 plus m2. In equation 7.1, x can be regarded as the mass weighted mean of x1 and x2. If the two particles have the same mass m1 m1 is equals to m2 is equals to m, then x is equals to m1 x1 plus mx2 divided by 2m is equals to x1 plus x2 divided by 2. Thus, for two particles of equal mass, the center of mass lies exactly midway between them. If we have n particles of masses m1, m2 up to mn respectively along a straight line taken as the x-axis, then by the definition, the position of the center of the mass of the system of particles is given by x is equals to m1 x1 plus m2 x2 up to infinity mn xn divided by m1 plus m2 plus up to infinity mn. Summation I is equals to 1 to n mi xi divided by summation I is equals to 1 to n mi is equals to sigma mi xi divided by sigma mi, where x1 x2 up to xn are the distances of the particles from the origin. X is also measured from the same origin. The symbol sigma denotes summation. In this case, over and particles, the sum sigma mi is equals to capital M is the total mass of the system. Suppose that we have three particles not lying in a straight line. We may define x and y axis in the plane in which the particles lie and represent the position of the three particles by coordinates x1, y1, x2, y2 and x3, y3 respectively. Let the masses of the three particles be m1, m2 and m3 respectively. The center of mass C of the system of the three particle is defined and located by the coordinates xy given by x is equals to m1 x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3, y is equals to m1 y1 plus m2 y2 plus m3 y3 divided by m1 plus m2 plus m3. For the particles of equal mass, m is equals to m1 is equals to m2 is equals to m3. So therefore x is equals to m common x1 plus x2 plus x3 divided by 3m, that is x1 plus x2 plus x3 divided by 3. Similar way we can find the y as well. Thus for three particles of equal mass, the center of mass coincides with the centroid of the triangle formed by particles. Results of equation 7.3a and 7.3b are generalized easily to a system of n particles, not necessarily lying in a plane but distributed in a space. The center of mass of such system is at x, y, z, where x is equals to sigma mi xi divided by m, y is equals to sigma mi yi divided by m, and z is equals to sigma mi zi divided by m, where m is equals to sigma mi is the total mass of the system. The index I runs from 1 to n. m1 mi is the mass of the ith particle, and the position of the ith particle is given by xi, yi, zi. Equation 7.4a, 7.4b and 7.4c can be combined into one equation using the notation of position vectors. Let Ri be the position vector of the ith particle and R be the position vector of the center of mass. Ri is equals to xi I cap plus yi j cap plus zi k cap, and R is equals to xi cap plus yj cap plus zk cap. Then R is equals to sigma mi Ri divided by capital M. The sum of the right hand side is a vector sum. Note the economy of the expressions we achieve by use of vectors. If the origin of the frame of reference is chosen to be center of mass, then sigma mi Ri is equals to 0. For given system of particles, a rigid body such as metal stick or a flywheel is a system of closely packed particles. So equations are therefore applicable to a rigid body. The number of particles in such a body is so large that it is impossible to carry out the summations over individual particles in this equation. Since the spacing of the particles is small, we can treat the body as a continuous distribution of mass. We subdivide the body into n elements and small elements of mass delta m1, delta m2 up to delta mn. The ith element delta mi is the taken to be located about the point xi, yi, zi. The coordinates of the center of masses are given by this. As we make n bigger and bigger and each delta mi smaller and smaller, this expression become exact. In that case, we denote the sums over I by the integrals. So here m is the total mass of the body. The coordinates of the center of the mass now are x is equals to 1 upon m integration x dm, y is equals to 1 upon m integration y dm, and z is equals to 1 upon m integration z dm. So r is equals to 1 upon m integration r dm. So r is equals to 0, so it is 0. Often we have calculated the center of mass of homogeneous body of regular shape like rings, discs, spheres, rods, etc. By using symmetry consideration, we can easily show that the center of mass of these bodies lie at their geometric center. So we will just stop here. In the next video, we are going to start with geometric center of a rigid body. Thank you.